Welcome everyone. In this video we are going to find the energy levels of an electron in a hydrogen-like atom using Bohr quantum mechanics. This video is the continuation of a previous video, so make sure that you watch that video from the cards right now, or you can access it from the descriptions part. Now that being said, I now want to find the formula for V, which is the speed of our electron. How do we do this? Well, in the previous video that I just mentioned, I showed that m, the mass of the electron, times its velocity, its speed, or times the radius of the orbit is equal to n, a positive integer, times h Planck, which is reduced h bar, which is reduced Planck constant. So we have this formula, and also in that video I also showed that V squared is equal to K, Coulomb's constant, times Z, the atomic number, times E squared, the elementary charge squared, the charge of a proton, or the magnitude of the charge of an electron, you can call it that, mass of the electron, and radius. So we got these two from the previous video, which I really suggest you watch, because otherwise this video is pointless basically. You need to know where these two come from. So in this case, I want to substitute for mr in this V squared equation. Well, how can I solve for mr? I can solve for it in the first equation. If I divide both sides by V, I am going to get that mr is equal to n times h bar divided by V. And now I am going to substitute this. So let's write V squared on a new line. We have V squared is equal to, we have K Z E squared. We would divide by mr, so let's just multiply by its reciprocal, which means we bring the V to the numerator, and n times h bar is going to be in the denominator. So we get this. Alright? And now if we simplify both sides by V, look at this. We found our formula. We solved for V. V is equal to Coulomb's constant times the atomic number times the elementary charge squared. Let's write it a little cleaner. E squared divided by an integer n times the reduced Planck constant. This is the formula for the velocity of our electron. However, actually the magnitude, we didn't specify in direction. So we want to now use this to find the formula for energy. And also a quick side note, we sometimes put a n here to denote that this changes with n. If we change n, we also see that V changes, so it is in a sense a function of n, alright? This is just a side note. So we want to find the energy, capital E. And since we are dealing with mechanical energy, it is going to be equal to K, the kinetic energy, plus U. Not U, but the potential energy U. Okay? Probably that wasn't confusing, but anyways, I wanted to point that out. We sum kinetic energy and potential energy to get the total mechanical energy. Well, what is kinetic energy though? Kinetic energy is equal to 1 over 2 mv squared. And look at this, what a coincidence. We have a formula for V squared. We actually have one for V. I just noticed that we didn't even, well actually, you know what, yeah, it was good that we solved for it. So we have formula for V, and when we square it, we can substitute it here. And let's do that then. For kinetic energy, we're going to have 1 over 2 mass and then V squared. I am just copying it from the line above. We get K squared, Z squared. Notice this, we have E. It was squared, we squared again. So E to the power of 4 divided by N squared H bar squared. Great. We got half of the job done. Kinetic energy is checked. Now comes the potential energy. What about potential energy? Potential energy in this kind of a case is going to be, since we have a nucleus and an electron orbiting it, we can use the potential energy for electric potential energy basically, because the only attraction between them is electrical attraction. Force of Coulomb force, basically. And we have a formula for this, and you can access that derivation from the cards right now, also from the descriptions part. This formula is going to be, it turns out that, and I proved that in the video you could find from the descriptions and the cards, this is equal to negative, not z, I mean k, and then the charge of the first one, which is going to be Ze, the charge of the nucleus, times the charge of the electron, that's where the negative comes from, and we put a square here, then divided by the distance between them. Okay, as I said, I proved this in a previous video. You can find it from the cards and from the descriptions part. It is important that you understand where this comes from. So we can, let's see, what should we do? We should substitute for R here, right? We need to substitute for R. And as a coincidence, in the previous video, I found the formula for R. That formula is, let me write it here and then we can continue on a new page. R is equal to, I am just copying it from my notes. We already derived this in the previous video. It is n squared h bar squared divided by mkze squared. Alright? So if we substitute this for U, the potential energy of our electron, we're going to have, let's even continue it here, negative k z e squared, and then we have R in the denominator, so let's just multiply by its reciprocal to get we have a k, so put a square on top of the k, we have a z, so put a square on top of the z, we have an e squared, so let's change the power of e to 4, and we divide by n squared h bar squared. If this step was a little fast for you, I really suggest that you try this yourself on a piece of paper, and you will see that this is what you get. And here you might be saying, oh, look at this, we solve an interesting thing. We have this crazy stuff here, bunch of quantities, but they appear here as well. They are the same quantities. Even the powers are the same. They are not different. Only the coefficients are different. We have -1 and we have a half for kinetic energy. Should we be surprised? No, not exactly. We shouldn't be surprised because at the end we are calculating energies, kinetic energy and potential energy. They are energies, so they should have the same unit. So it makes sense that we have the same power for each of the quantities, okay? Because otherwise, how could we get the same unit? All right, I hope this is making sense. So we could have even guessed what the quantities should be, but there was no way that we could get the coefficients of 1/2 and -1 without carrying out the calculations. Okay, so I just wanted to point this out. And now we're ready. Let's sum it up for E. E, the total energy is going to be K, kinetic energy, plus U, the potential energy. And we have formulas for both. Right? We have formulas for both. And how is it going to be? Well, should I write it? I don't really think I shouldn't write it. This is a 2 here. And if I multiply the top and the bottom by 2 in the potential energy formula, I will have a 2 here and a 2 here. So we have the same denominator for both energies, which means we will keep the denominator. We will have 2, let's see, what was it? N squared, h bar squared. We have negative, we have simply, let's see, we have -2 on the top, we have a +1 on the top for kinetic energy, so we get -1 basically. And I don't even need to put the negative, I don't even need to put the 1, but I need to put the negative, of course. And we're going to have other quantities, which are k squared, let's see, okay, I got this. Z, was it squared? It turns out I didn't got this. Okay, z squared, and then e raised to the power of 4. And this is actually the formula. This is the energy levels of an electron in a Bohr, using Bohr quantum mechanics in a hydrogen-like atom, which means there is only one electron, but the nucleus can contain more than one proton. It is represented by Z. Perhaps we have an ion of helium, we have an ion of lithium. That is possible. Alright, this is the formula, and we could talk a lot about this, and perhaps in a future video I can mention what this formula is telling us, but the one thing that I want to show here is that we have n here, which is an integer. So we in fact have E subscript n. Notice this. Energy, when we think of energy, we think of it as continuous. Right? In daily life, you can increase the gravitational potential energy of a book perhaps by raising it slowly. And when you raise it, you always think of it as a continuous process. It is like going a ramp. It is continuous. You may have gradual increases, but it is continuous, right? I repeated myself, but I think this is pretty much apparent because we encounter this in daily life. However, this formula tells us in quantum mechanics for particles like electrons and for other particles, energy levels are discrete. It is like going up a staircase, not a ramp, but there are certain energy levels that you can have for certain n values. Okay, perhaps this one corresponds to n1, for 2, 3 goes up like that. And also notice one thing as well. This is going to be the last point that I make today, which is very important. When we increase n, let's say we have E1, which corresponds to the case where n is 1. When we increase it to 2, we divide by 4. So we perhaps have something like this, okay? E2, and it is going to be greater than E1 because we have a negative sign here. When we divide by something great, we get something that is less negative, so it is a much bigger number. It's a bigger number, basically. When we divide it by 3, though, when we have 3 for n, we divide by 9, because 3 squared is 9. So from here, we had a 4-time increase, right? We divide by 1, then divide by 4. But this time, we only divide by 9. We don't divide by 4 times 4, 16. No, we divide by 9. So the gap between E2 and E3 is smaller than the gap between E1 and E2. And for E4, it is going to be like that. The gap gets smaller and smaller and smaller. So this means, in a sense, energy levels converge. They are becoming closer to one another, and you might have heard this is the case in a chemistry class, and now you know that this is in fact the case because we just use math and physics to show that energy levels are discrete and that they converge. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care. I know I ended the video, but I just remembered a very important thing that I forgot to tell you guys. This was the 100th video on this channel. I can still remember the first video, which was proving the inverse Pythagorean theorem, and from that video there has been others, and now we're on the 100th video. So it is really special for me. I want to thank everyone who have been following me up to this point, especially 2 special thanks goes to my mom and my dad. I know that they have been my number 1 and 2 followers, subscribers throughout this journey. I hope that we will see much more videos. I really don't plan to stop at 100. This is just the beginning. Sky is the limit. No, anyways. I hope you like the videos and enjoy it. And as I said, I will be uploading more videos